All right, well, we're going to get started. I'm Lisa Rozmyn. I'm the assistant director. I'm just saying that because my boss is in the audience. I'm the assistant. I know, it really did, didn't it? I'm the assistant director of the Washington Stormwater Center, and I want to welcome you all here to our presentation today, using research outcomes to inform solutions for highway runoff. Um, I want to let you all know that we are recording today, but the question and answer session will not be recorded, so you won't be on the video. Okay, so with that, I'm going to introduce our speakers today. Ben Leonard is a PhD student at WSU. He's part of the School of the Environment, and he's going to be talking about the compost amended, thank you, bioswale system. Sorry about that. Lane Maguire is a master's student with us at WSU, and she's going to be talking about bioretention longevity. She's got a great study about that. And Claire Duchet is a postdoc with us at WSU, and she is an aquatic toxicologist. Oh, and she's going to be talking about the permeable pavement study. All right, so I'm going to just briefly go over the DOT permit. Do we have anybody from DOT here today in the audience? I knew it. I knew it. Oh, pressure's on. Pressure's on. All right, so the biggest change to the new permit that was just issued on April 5th is that the stormwater management plan is now a standalone document, and that is a good thing because if they want to make any changes to their stormwater management plan, they don't have to do a modification of their permit. They can just do it as a standalone document. The permit coverage is the same. It's the areas within those MS4, Phase 1 and Phase 2, and then all the TMDLs that they have as well. So that's a pretty big area to cover. And it's these areas of highways, ferry terminals, et cetera, that they have to manage the stormwater from. So DOT is responsible for more than 7,000 miles of roadways and highways throughout Washington state, and that's a lot of miles. There's a lot of talk and research about polluted runoff and the effects to aquatic life, in particular coho salmon. And there's been a lot of, DOT should step up and do all these things. They are doing a great job, and they have a huge job ahead of them. So I wanted to mention that. So who's to blame? And I like to blame the ancient Romans, because the ancient Romans are the ones that invented these darn roadways to begin with. It's not DOT's fault. They did not invent roadways. But in all seriousness, it's the pollution comes from all of us that drive our cars and the lifestyle that we have. So we are all responsible for that pollution. So we're trying to find solutions along with DOT to these pollutants and the effects they have on our aquatic life. So they work hard to protect Washington's waters by updating and improving their stormwater management plan and their highway runoff manual, installation, operation, and maintenance of all those BMPs that they have to deal with. And they do lots and lots of cooperative research with us and others under the SAM banner as well. And we are participating in some of that with the testing of BMPs for effectiveness. So with that, I'm going to turn it over to Ben, and he's going to talk about his CABS project.
Great. Hey, thanks for the intro, Lisa. That was fantastic. Yeah, I enjoy any mention of the ancient Romans. So I'm going to be talking real quick. We're all doing study overviews. It's going to be around like 5 minutes, so we're not going to get too deep into the nitty gritty here. But this is a study with WSDOT that we've been doing for the last 2 years. And specifically, we're working on looking at these compost-emitted biofiltration swales and looking at some parameters in addition to the tape parameters that may change their effectiveness over time, and then also like what makes a good biofiltration swale, what are the components that go into making these work. And what they are, just for those not in the know, is more or less grassy buffer strips that are maybe easier to install than other stormwater BMPs along the side of roadways, and they're tilted at an angle to where water coming off the roadways that maybe has gathered certain contaminants can move slowly and through various actions such as settling and biotransformation as well as sorption. You can actually remove some of these pollutants in the effluent water. And there's also flood considerations and how these can also be used for just kind of the physical water and how to keep it from going all over the place, but we're specifically looking at the actual pollutants here. Adding compost to the top of these guys, one of the main reasons for that is that you have much more organic matter there. It's going to increase the amount of grass and vegetation growing. It's also going to increase the pore space within the media that can be used for sorption. So what we have is some previous data from the State Route 518 cabs. That's pretty close, actually, to where we stand right now, a little south or north of the SeaTac Airport. And these are data from Herrera 2011. They looked at the influent effluent of a normal bioswale, so without compost, and then when you add compost, how does that affect the removal of certain contaminants? And specifically, you can see that with total copper and total zinc, there is quite the significant removal effect. Maybe less pronounced with some of these other contaminants, but the top three there with copper, zinc, and TSS, those are the main contaminants that are removed. We also have a study site up at State Route 520, which is kind of a characteristic spot for collecting stormwater for many of our other experiments. The idea we had is kind of replicate some of these results for 518, but do it in a laboratory controlled setting. So we went to, well, I'm based out of the WSU Puyallup Research Extension, and so we created a artificial bioswale there. You can see that in the lower left-hand corner, and we would collect water, and we've done several events now. You can see there's actually 6 listed here, and what we'll do is we'll truck it down from these from the collection ports at State Route 520, put it through the bioswale, and collect water coming out at different ports along the way, so you get how length might affect the removal of contaminants, and then also at the same time how fast water is going through the bioswales, how that might also affect the removal of contaminants. And we specifically are looking at something called hydraulic retention time, which is how long water stays in these systems, and that's going to affect how much removal you get. So this is kind of our sampling procedure. You take a big tote, you pump water through, you collect it at different ports, and then in the lower right hand, that's the final effluent port at 50 feet. So that's half the length of a field bioswale installation. And now real quick, some results for PAH removal. We're looking at specifically here the system at 518, and there are 2 ports there, one at 25% down the total length, so that's 25 feet because this is a 100-foot installation, and then the 100% effluent. So in general, there's pretty great removal, but it's not necessarily a linear relationship. You don't see that the 25% port is, a quarter of the actual removal of these contaminants. And then we are also looking at bioassays. So what physical markers might indicate pH removal? One thing is zebrafish heart area. If you expose these embryos to pH contaminants, the heart tends to swell after 48 hours, and you can gauge the effectiveness of removal from a bioassay perspective that way. Finally, I'm just going to do a quick slide on zinc removal, and you can also see a similar trend where you get a lot of removal within the first, 25% of the total length, but that's not necessarily a linear relationship. The kind of result from a management perspective would be maybe you don't need to make them quite as long, and you could do more short bioswales. But then one thing to point out is you can see there that sometimes you get these large net exports of metals, and that basically shows that these systems can trap metals, but they can also release the metals that they've trapped in one fell swoop. So anyhow, I'm gonna move this presenting wand over to Lane.
Hi, I'm Lane. So I'll be talking about a little bit about my research project, which is looking at the longevity of bioretention depths for preventing acute toxicity from urban stormwater runoff. And so this project is a part of the Department of Ecology's Stormwater Action Monitoring Program. So for this study, experimental columns comprised of a 60-40 sand compost mixture were constructed to test the effectiveness of varying depths of the bioretention soil mixture. So you can see, okay, we have depths ranging from 6 to 18 inches, and then we have one 18-inch column which just serves as a clean water control, and 3 replicates of each of those columns. So 18 inches is the depth that's required by the Department of Ecology in their Stormwater Management Manual for Western Washington. And so the objective of this study is to determine the minimum depth that will still be successful for preventing acute toxicity to aquatic organisms and improving water quality. And so to evaluate the longevity of these bioretention columns, stormwater runoff will be applied under an accelerated schedule in order to try to simulate 10 water years over just 2 calendar years. And so each water year spans about 2 months of a calendar year. And to account for the discrepancy in thermal conditions between the simulated water year and the actual calendar year, a thermal regime will be established to more closely align the climatic and microbial conditions of the simulated water year with those of a more natural environment in a typical calendar year. Okay, and so here in that left column, you see each of my 10 water years. Each water year is comprised of 6 events. And so for the first event and the event ending each water year, we'll be subsampling water from the influent and effluent from each of the columns to look at analytical chemistry. We'll also be subsampling, again, from the event ending each water year, for the first event and the event ending each water year to look at toxicology with the zebrafish embryo model. And then also for the first, middle, and last event, looking at toxicology using juvenile coho salmon. And so we'll begin with the 5 bioretention depths, and then at the end of water year 2, we'll be reducing the number of depths from 5 to 3. So those depths that we choose to then move forward with for the remainder of the study will be those that are the best performers in terms of improving water quality and reducing acute toxicity to those aquatic organisms. And so through the study, I hope to answer 2 main questions. The first is how long can the 60-40 sand compost mix prevent toxic effects to aquatic organisms? And the second is what soil depths are necessary to provide biologically significant improvements in water quality. And so right now I'm doing some baseline monitoring to try to determine whether any of my bioretention soil media components themselves are a source of any organic or inorganic analytes. And so each of my bioretention soil media components, so that's the sand, compost, gravel, and mulch, are being leached according to this E.P.A method, the synthetic precipitation leaching procedure. And so that leachate will then be analyzed for a variety of things, including pHs, metals, nutrients, and some other conventional parameters. And then that leachate will also be used for toxicology testing using the zebrafish embryo model again. And so my next steps, column conditioning. So prior to the application of any stormwater to these columns, we'll just be applying clean lab water to try to determine the chemical composition of water that's actually passing through these columns. And then I'll move on to the actual stormwater dosing and begin that accelerated aging process. So next I'm going to pass it over to Claire.
Hi everyone. So I'm going to talk to you about the, oops, didn't do anything. The mitigation of stormwater toxicity with permeable pavement. So actually I will be brief because I don't have any result to present you yet, but I will just present you the objective of the study and how we'll try to answer the questions. We have 2 main questions. The first one, maybe the most important one, can we decrease the toxicity from stormwater runoff using permeable pavement? And the second one, in the long term, is there any toxicity leaching from those permeable pavements? So we got the opportunity to get a course from the Composite Materials and Engineering Center in WSU in Pullman. Course with or without carbon fiber. So we got from them 16 cores, 4 asphalt cores with carbon fiber, 4 without carbon fibers, 4 concrete cores with carbon fiber and 4 without carbon fiber. We aim to collect 5 storms and to run five storms through the cores. We run in parallel stormwater and control water, so we'll have 2 replicates per treatment for each type of cores. We'll collect the influence and effluent, and we'll to run some chemistry analysis like pH, dissolved oxygen, pH, bacteria, total suspended solid, dissolved organic carbon, nutrients, and metals. But we'll also run some toxic tests from influent and effluents to look for the sublethal effects on the zebrafish embryo. We look for the abnormalities on the development, and also the sublethal effects on the crustacean Seriodaphnia dubia. Look for any effect on the survival, reproduction, and growth. So stay tuned for the results. I hope we'll run it soon. Probably the first one should be the next storm coming, so who knows, maybe next week. Thank you very much.